Hi there. In this video, we're going to keep going in Chapter 6, and we're going to do Section 6.2, Inference for a Mean. So now we're doing single quantitative response variable. So let's get started. So first we're going to look at the distribution of sample statistics. When we are looking for a population mean, that's our parameter, so it's mu. The central limit theorem says the distribution of sample means follows a normal distribution if the sample size is large enough. And so if we have a very large n and we know the mean and know the standard deviation, it turns out that the distribution of sample statistics, so the sample means, is normally distributed with mean mu, which is the mean, and the variability given by the standard error. So there is some tricky stuff going on behind the scenes. You have a formula sheet. I posted an announcement in Canvas, if you haven't seen it, that links to the new formula sheet. So if you missed it, make sure you double check the formula sheet. I want you to keep the formula sheet in front of you when you're doing this stuff. So this is how it works, right? If we know mu, right, and let's go back one slide just so we're clear on this. We have to know the mean and know the standard deviation. Generally speaking, this doesn't happen very much in the types of studies we've been looking at. If you were working in a factory or something and the machine, all the parameters were known for some sort of machine, then you would use this distribution. Most of the studies we've seen are studies about either people or animals, right? And ordinarily we don't know the means and standard deviations of those populations. So here, again, what we're saying is that if we know sigma, then the standard error is given by sigma over square root n. And the other thing we need in order for this to be true, right? In order for this statement here at the bottom to be true, we need a large sample, or the data itself has to be normal. So what's really going on here is that the rules governing when we can use these formulas and when we can't depends on the populations being normally distributed. But we don't know anything about these populations. Even if we know the mean and standard deviation, we don't know if the populations are normally distributed. There are ways of testing it. We don't cover it in this class. So what we do instead is we just look at the data. If our data set appears normal, then we treat that as the population being normal. Or we need a large sample, right? So that comes from the central limit theorem. So if n is greater than or equal to 30, or the data is normally distributed, then we can use this. And if one of these is satisfied, or both, then the standard error is given by this formula. So if random samples of size 1,000 are drawn from a population with mean 28 and standard deviation 5, find the standard error of the distribution of sample means. So the idea here is that we know the mean, we know the standard deviation. And the idea here is that if we take large enough samples, then we can use the central limit theorem, right? And that's what it says here, right? Here, for example 1, we're taking samples of size 1,000. That's clearly bigger than 30. So we've achieved this condition. And now we can use this formula. So the standard error is just sigma over square root n. So you just plug everything in and you get the answer. So it's 0.158. Go ahead and check that you can do this on a calculator. Make sure you can get the same answer. Again, when you're using the TI-84, you want to build the fraction first. Right, so there's 5, and then you want to put that square root in the denominator like that. Right, and just type it in one shot like that. So make sure you're typing it in the way it looks in your, in your by hand calculations. Now, when we don't know the value of sigma, we can use the sample standard deviation S to estimate the standard error. When we use the standard error based on S, the standardized sample means approximately follow a t-distribution. So this is a new distribution we haven't seen yet, with n-1 degrees of freedom. So this is another statistic, this degrees of freedom. For small, and then the second bullet, for small samples, so n less than 30, the t-distribution is only a good approximation if the underlying population has a distribution that's approximately normal. That's what we saw on the previous couple of slides, right? We need either large samples or normal population, or both. If we know the standard deviation, it's the distribution of sample means is normal. If we don't know the standard deviation, we use the sample standard deviation, and then we can't use a normal distribution anymore. We have to use what's called this t-distribution. So we're going to talk about the t-distribution for a while because it's a new type of bell-shaped curve. So the main feature of the t-distribution is that it does look bell-shaped, but it does have a different shape for different values of df, right? So here's the df's over here. So you can see that if your df is 2, it's this blue line here. And you can see that it kind of looks normally distributed, but the tails are much thicker, right? The edges of the distribution are much thicker, and the center is much thinner. Well, what happens as we increase the df? Well, you can see if your df is 5, it's this red dashed line. So the center is starting to thicken out, and the tails are starting to thin out. And then once you get to about 30, you can see the difference between a df of 30 and a df of 1,000 is very, very close, right? It's these purple and green lines here. So once you get to about 30, the shape doesn't change too much. So that's one reason why our large sample cutoff is around 30, just because the shape of this distribution doesn't change that much. It's not the only reason, but it's one reason. So that's kind of the key point for the t-distribution, is if the df is large enough, then you can just replace it with the normal distribution according to the central limit theorem. One more thing I want to point out, it's on the previous slide, is that the sample size determines the degrees of freedom. So here, if our df is 2, the t-distribution is the distribution of sample statistics if we take samples of size 3 from a normal population. You always have to have a normal population or large samples. If your df is 2, your samples are size 3, that's not a large sample. And again, right around 30 is kind of the cutoff where most people are willing to accept that the t-distribution is actually a normal distribution. It's correct within 2 decimal places for most of the things we're going to look at. So let's talk more about the t-distribution. What we use it for is when we don't know the population standard deviation, which for almost everything we've done in this class so far, we really don't know the population mean or the population standard deviation. So we take a sample. That sample gives us a sample mean. That sample gives us a sample standard deviation. And that's why we use that degrees of freedom calculation, because the sample mean uses the sample standard deviation uses the sample mean as part of its calculation. So we're using the sample mean to compute 2 different statistics. So that's where that degrees of freedom comes from, in that we have to take into account that the sample mean might not be equal to the population mean. And because we're using it to compute 2 different things, it causes our distribution to be a different shape. At the end of this video, I'll show you some stat key that explains where this stuff comes from. And also at the end of the video, I'll show you some of the calculator shortcuts, as I've done in the previous 2 videos. All right, so in section 5.2, we saw when the distribution for the sample statistic is normally distributed, the confidence interval can be formed using this. But what we just saw is that we don't know z star, because z star is based on a normal distribution. And the normal distribution we can only really have if we know mu and know sigma. So down here at the bottom, we explain what to do. If we don't know mu and sigma, we use the percentiles based on a t-distribution. So that's the third big change from chapter 6 from chapter 5, right? What is a large sample? Yeah, so there were three things that we wanted to cover, right? You know, what determines a large sample? And then we talked more about the central limit theorem. And then the third thing is, what is this t-distribution, right? So here's our formula summary. So whenever you're doing a confidence interval, in this section, single mean, so single quantitative response variable, large sample size or normal data, that we've already talked about, but we're going to talk more about it. The standard error, notice it's just s over square root n instead of sigma because we don't know sigma. Margin of error is just t star times s over square root n, right? Remember, the margin of error is everything on the right side of the confidence interval. So that hasn't changed since chapter 3. And the confidence interval is x bar plus or minus t star times s over square root n. For some reason in the PowerPoints, this x bar never shows up. It just has a little tiny bar. I don't know why that is. Microsoft doesn't seem to care. But that is an x bar. So calculations in this section resemble other sections we've seen, but we need to compute t star values for confidence intervals. Although some graphing calculators can find inverse t values, not all of them can. If you have a TI-84 plus, you can use the inverse t function. So I'm going to talk a little bit about the inverse t function as we go through. If you want to use stat key, you can. And all the examples in the PowerPoints use stat key to find the t star values. So I'm not assuming that anybody has a TI-84 plus, because the 83s and some of the Casio calculation stuff, I don't know if they'll do inverse t's. So if you want to do an inverse t, this is how you do it. It's exactly the same as the inverse normal that we saw in chapter 5, except you don't type in the mean and standard deviation. The t-distribution, the mean is 0, and the standard deviation depends on the df. So what we're doing is you're not putting the mean in at all. The mean is always 0 for the t-distribution. And you just put in the df value instead, because computing the standard deviation from a t-distribution is not very fun, so we don't do it. Instead, we just type in the df. So you just put in the area to the left of your endpoint, like you did for the inverse normal, and put in the df. And we'll see how to do that. We'll get into some examples here in a sec. So what are the endpoints for 95% confidence interval of a t-distribution with 29 degrees of freedom? So 29 degrees of freedom, that would come from a sample of size 30, because, you know, the df is n minus 1. So what we have to do is kind of draw the thing out or go into stat key. And because we're doing an inverse, you could draw it, you know, by hand, right? So think about what this would look like. Here, let me clear this guy out. Right, think about what this would look like. So it kind of looks like a normal distribution, right? We're just not going to label the standard deviations. We're only labeling the center, right? And then notice it says 95% confidence, right? Well, it's, again, very similar. So it's still like the middle 95%. So it's going to be around plus or minus 2, right? So we're looking for, you know, we're looking for t star. And then over here, this is negative t star, right? So that's what we're looking for, right? So this is how you do it. You can go into stat key, and it's exactly the same as what you did with the inverse normal, right? Here, I'll show you. So it's in theoretical distributions T. The instructions are in the PowerPoints, but I'll just show you. And then you type in the degrees of freedom. We had 29. So there's your degrees of freedom over there. It's a confidence interval, so it's two-tail. Change that to 0.95, and you're done. So this one was done for you. So if you had to do a 90%, 98%, just change the middle number, just like you did in Chapter 5 with the normal distribution. So this looks really similar to a normal distribution, right? Or you can use your calculator, right? So if you have a TI-84, right? Again, instructions are in the PowerPoints. Down here, it's just inverse T. You have to type into the area to the left. So we want this T star or this minus T star. It doesn't make any difference. So you either type in 0.025 and make it negative, or you add these two regions together, or you do 1 minus this, trying to find everything below this number. If this is 0.025, this is 1 minus 0.025, right? So that's going to be 0.975. Then you type in the degrees of freedom. We know it's 29. Right, 2.045. So it's however you want to do it. On a test, either method is fine. So you're not using a ton of stat key on the exam, on the third exam or the final. You're not using a ton of stat key. But if you want to use stat key, you can. I still think the graphing calculator is a little quicker for most situations. And so down here at the bottom, it explains what we're going to be using this for. When these endpoints are used to compute a 95% confidence interval for mu with a DF of 29, now we know T star. And so every time you do a confidence interval, you have to do a separate T star calculation. You can do it on your graphing calculator if you have a TI-84 Plus, or you can do it in stat key. But it's always the same steps, right? Here's your stat key again. It's always the same steps. Put in the DF, change this to your confidence level, and your T star will be plus or minus these numbers. And there's the instructions how to do it in stat key. Again, everything's in your notes. I went ahead and showed you that, so I'm not going to spend any time on it. All right, let's do another confidence interval. So now we're going to kind of do one all the way through. So using the sample results, X bar is 10.9, S is 4.8, N equals 30. Assume the results come from a random sample from a population that is normally distributed, right? Have to have a normal population, or we have to be able to see the data. Round your answer for the point estimate to 1 decimal place. That's done for us. And your answers for the margin of error in the confidence interval to 2 decimal places. And as you can see, parts A, B, and C look pretty typical. This is what problems look like in earlier in Chapter 6, Sections 6.1 and 6.3. Best point estimate, margin of error, and confidence interval. So what's the best point estimate for mu? So hopefully you said it out loud, and hopefully you said it quick. It's 10.9. Right, it's X bar. X bar is our estimate for mu. What about the margin of error? So I gave you a template at the end of chapter 6.1. The end of section 6.1, I gave you a template. And the template says no matter what you're doing, always do the sample statistic first, then always do the standard error first. So what's the standard error in this problem? Well, according to the formula in the table from a few slides ago, the standard error is S divided by the square root of N. So that's what you type in, right? We already did the t-star, right? We did that in example 2. So s over square root n, 4.8 divided by square root of 30 is 0.876. Go ahead and check that on your calculator. Make sure you can get it. Now the margin of error is t star times the standard error. We already computed this as a separate problem, but if the sample size was something different, you'd have to go back into StatKey or go back into your calculator and recompute t star for every problem. These are not like z stars where you just memorize them or have a nice handy chart. So if our sample size was a little bit different, t star would be different and our margin of error would be different. So the margin of error is t star times s over square root n. Again, now you can round everything to 2 decimal places because we're ready to do the confidence interval. So the confidence interval is the sample statistic plus or minus the margin of error. And so you get 9.11 to 12.69. Go ahead, make sure you can get all these numbers. Pause the video if necessary and make sure you're getting all the same values. This is what the exam is going to look like. Right? Not a ton of it, but enough of it that it's worth a lot of points. Because there's only 7 sections on exam 3. And almost all of it is number crunching. Whereas so far in this class, very little of the class is number crunching. Third exam, almost all of it is number crunching. That's why you have those formula sheets. All right, so let's talk more about these conditions to use the t-distribution. We briefly mentioned them in the tables earlier in the slides, but we didn't talk about where they come from and why we need them. So in order to use the standard error formulas, we need to check that one of the following 2 conditions is satisfied or both. The sample is large or the sample is approximately normally distributed. So large sample, that does 2 things. That makes our t-distribution turn more into a normal distribution when n is around 30 or larger. The other thing it does is it makes the distribution of sample statistics not just normal, but very bell-shaped. And then in 2, the sample is approximately normally distributed. So if the sample itself is bell-shaped, it doesn't matter if the sample is large. So what we have to remember is that the only real condition is condition 2. That's the one we're really checking. But when the sample is large, the distribution of sample statistics becomes more or less bell-shaped. So it doesn't matter if the sample is normally distributed. And if our sample is small, we need to check that the data are symmetric and have no outliers that might indicate a departure from normality. So again, if the sample is large, it doesn't matter what it looks like. If the sample is small, we need to check this. So how do we check approximately normal? Well, basically, we talked about this earlier in the class in Chapter 2 when we started looking at dot plots and histograms. And we said, how do we know if something's normally well, at the time we just called it bell-shaped, right? How do we know if something's bell-shaped? Well, it just has to be approximately bell-shaped. We don't insist on an exact bell shape in order to use a t-distribution. It just has to be close. So here are 2 good examples. Both of these examples are small samples. Small samples need to be checked that they're approximately normal. So notice here that's not really skewed and there's no outliers. Small sample, not skewed, no outliers. That tells us that we can use the t-distribution for inference for this data set. What about over here? Small sample, 1 outlier, severe skewness. Well, this tells us we can't use a t-distribution, but we could use a bootstrap distribution or randomization distribution. And that would require us to go back and look at chapters 3 and 4 and check those conditions. So you might be wondering why this happens. Well, let's go into StatKey and look it up. So what I'm going to do here is I'm just going to do a sampling distribution for a mean. Just going to show you. Actually, let's do a bootstrap distribution because it's easier to build those. All right. So you guys don't have to do this stuff on the homework or anything, but I think it's important to understand why this stuff works. All right, here we go. So what I'm going to do is I'm just going to type this data set in, right? I'm just going to edit the data. So it's 3, 4, 4, 5, 5, 5, 6, 7, right? So you can see our data over here, right? And if we generate a bunch of samples, so I generated 1,000 samples. So this is using bootstrapping. So this is very similar to what we did with the ants on a sandwich, right? Very similar. Back in chapter 3. Definitely bell-shaped, right? And not just bell-shaped. It turns out that it's a t distribution. Now, what happens if I use this other data set over here? Well, I don't want to type in that whole data set, so let's just make one of these an outlier, right? So look, I just made a big outlier over here, right? So I just changed that 7 to a 23. So you can see that a bunch of weird stuff happens, right? So this is why we can't use the normal distribution, or sorry, why we can't use a t distribution when we have small skewed data sets. Now, what if we have a large skewed data set, right? Well, there's some of them built in here, right? Right, so here's one that, I don't know if this was homework or if it was on, I think this was a homework problem. This is a large sample of size 500. You can see there's some outliers over here. But the distribution of sample statistics when I do a bootstrap is quite normally distributed, right? I mean, and you can just keep clicking it. It really fills out nice here. There you go. So that looks like almost a perfect bell shape. So even though this is skewed, and there's some outliers over here, because it's a large sample, it doesn't matter if it's skewed. So that's sort of why we're using these conditions, right? So that's where these conditions come from. Small sample that's normal, good to go. Small sample that's skewed, not good. Large sample, doesn't matter what it looks like. Large samples are always good. And again, our large sample condition is right around 30. All right, let's keep going. So a common question when designing a study is how large a sample should we collect? Well, this is very similar to the problem we saw in section 6.1. What sort of margin of error do we want? How much confidence do we want to have? And how much variability is there in the population? So here's the formula. If we want to estimate a population mean to within a desired margin of error, with a given level of confidence, we should select a sample of size. So let's talk about all this stuff here. So we know what Z star is. You might be wondering why it's there, but we'll talk about that. But we do know what Z star is. We know what a margin of error is. We don't know what sigma tilde is. And then we square the whole thing. Okay, so sigma tilde is an estimate for the standard deviation of the population. Now you might think, well, why can't we just use the sample standard deviation? Well, it's the same problem we ran into in section 6.1 when we did problems like this. If you haven't taken a sample yet, you don't have a sample standard deviation. This needs to be determined before the sample is taken. Z star depends on the confidence level. Margin of error depends on the practical significance. But sigma tilde is some sort of estimate for the variability in the population. And that's tough to kind of come up with off the top of your head. So when we make a reasonable guess for sigma, there's 4 things we can do. We're really only going to do one of these, but in the real world, there's 4 things you can do. You can use the standard deviation from a previous study or a sample from a similar population. So that's by far the most common use, or the most common way to get sigma tilde, is just look at a previous study or a sample from a similar population. You can take a small pre-sample and use its standard deviation. So if you're thinking your study might be hundreds of people, go out and take a sample of around 10 people. The standard deviation shouldn't change too much, so that would be a good estimate. You can also estimate the range, and sigma tilde can be the range divided by 4, right? So if you remember the range from chapter 2, this is a good way to estimate standard deviations. And we actually did this back in chapter 2. We would look at the entire dot plot, try to estimate like the middle 95%, and sort of divide by 4, right? That's how we did it. And then make an educated guess for sigma tilde. When in doubt, use an estimate or guess on the high side. That's if you have absolutely no idea what it is, just pick a number and see what happens. It doesn't seem very scientific, but this is how it's done. So we're going to use bullet 1 when we do problems. What sample size is needed to give a margin of error within 2 in estimating a population mean with 99% confidence, assuming a previous sample had S equals 3.6? So here we're basing it on a similar study. So we're kind of assuming that we're going to be doing the second study in a series, or we're replicating somebody else's study. Well, the margin of error is 2. We need 99% confidence. So that tells us Z star is 2.576. And sigma tilde is, of course, 3.6, because it is a standard deviation from a previous sample. Right? So there's all of our information. Plug everything into the formula. Go ahead and crunch this up on your calculator. Again, you want to make it look like this, right? So we need a squared, so go ahead and build some parentheses. So I like to just build the parentheses like that. So 2.576 times 3.6 over 2, and then just square it. And then always round it up. So even though it looks like that should be rounded down, round it up. And the reason you round this value up is the same reason that in section 6.1 we rounded that value up. This is the only time that I've ever seen in math that you round up for these sorts of calculations. For all other calculations in this class, you will round normally. All right, let's keep going. So next we're going to be doing p-values. Same sort of thing, except this time we're going to be using the t-distribution, not the normal distribution. So we're going to be using the tcdf command on the calculator instead of the normal CDF. And you type in left endpoint, right endpoint, df. Again, you don't need to type in the mean and standard deviation. The mean of the t-distribution is always 0, and the standard deviation is based on the df, so we just type in the df. Everything else is the same, right? Left tail, right tail, two tail, and that sort of thing. We do the same that we've done so far in this class with normal distributions. Here's the instructions how to do it in StatKey. I'm only going to show you how to do this on the graphing calculator because the StatKey is the same stuff you've seen before. All right, so area under a t-distribution. Assume the sample is a random sample from a distribution that is reasonably normally distributed, and we're doing inference for a sample mean. Find the area on a t-distribution above 2.3 if the sample has size 8. All right, let's use the graphing calculator first. Now, if you want to draw the picture, you can, but we know that this is left tail, two tail, right tail stuff. So I'm not going to use a bunch of time drawing all these pictures. I assume by this point, after what we've done in Chapter 5 and what we've done so far in Chapter 6, that you guys can draw the pictures of these distributions. And when you're doing a t-distribution, you don't have to label the standard deviations because we don't know what it is, right? We don't know the standard deviations. So the idea here, so this is, we're going to do TCDF, so it's number 6. We want to go above 2.3, so 2.3 is our lower. The upper, just pick a big number, doesn't matter, 10,000 is fine. The DF, well, the DF is just 8 minus 1, right? It's always the sample size minus 1. And always round to whatever you're instructed to round on the homework. So in this case, I rounded to 3 decimal places. And then stat key is very easy for this. I'll show you how to do this one in stat key, but I really don't want to spend a ton of time in stat key. Theoretical distributions T. Degrees of freedom was 8 minus 1, which is 7. We wanted the area above 2.3, so it's a right tail. Change that to 2.3. Right, so that's your cutoff value. And you can see that if you were to draw it by hand, this is what your picture would look like. Right, pretty good stuff. So nothing too different from the normal distribution stuff. All right, last thing, hypothesis tests. And in section 5.1, we had a generic formula that when the randomization distribution was normal, we computed a p-value using the standard normal distribution and the standardized test statistic. And this gave us a z. So in section 6.1 and 6.3, we had a z distribution. Now, when we don't know the population parameters, the test statistic just switches over to a t-distribution, but it has all of the same features. So what we do is, on the right side, everything's the same. This is still going to be x bar. This is still going to be mu 0. And this is still going to be the standard error that we defined earlier. It's just sigma over square root n, or in this case, since we don't know sigma, it's going to be s over square root n. So you get this. So we still need large samples or normal data, so you have to check that. The standard error, same thing that was given in the confidence intervals. And the standardized test statistic, again, given by... now this formula is actually the same one we saw in chapter 5, except because we're using S to compute the standard error, it's a t-distribution. And now this is going to be tricky when you guys are taking exam 3 or doing the adaptive practice. If you're given the standard error, this is a z distribution. If you're computing the standard error from sample data, it's a t-distribution. All right, let's do one of these. Is that right? Yep, let's do one of these. Use a t-distribution in the sample results to complete the test of the hypotheses. So we're using a 5% significance level, and we have a random sample, and we're going to assume the underlying distribution is normal because our sample size is 14. So we're going to test mu equals 6 versus mu greater than 6. X bar is 10, S is 7, N is 14. All right, let's do it. So what we're going to do is we're going to follow the guidelines that I presented at the end of the 6.1 PowerPoints, right? Sample statistic first. So what's the sample statistic here? Hopefully you shouted it out. It's X bar equals 10, right? Now you might have to compute this by hand, right? In this particular case, it's given. Next thing you want to compute is the standard error, okay, right? So we're going to compute the standard error and the null parameter value. and then the test statistics. So the standard error using the formula is S over square root n. 7 over radical 14 is 1.8708. And of course, we need the null parameter. The null parameter is given here, right? It's in the null. It's the number in the null hypothesis, so it's 6. And why am I keeping 4 decimal places here? I'll show you. So your test statistic is just plug everything into the formula. X bar minus the null parameter over the standard error. It's a t. So 10 minus 6 over 1.8708 is 2.14. If your calculations contain intermediate steps, keep extra decimal digits. So let me show you why this is an issue. We've talked about this before, but we never really knew why. So let's say you round this to 1.87, right? And then you want to go calculate, 10 minus 6. And let's say you computed the standard error at 1.87. This happens all the time. So it's still 2.14. But depending on how you round this, because this is really close to 1.87, but just depends on how you round it. That if you cut these off, so for this particular one, it's fine if you round it. But sometimes rounding off an extra half digit can actually change this answer. So watch for that. It happens more in section 6.3 and 6.1, but still be aware of it. All right, next up. Oh, I forgot. So we found the standard error. We found the test statistic. Now we go back and we look at this. This is a right tail alternative. So we're going to go TCDF. All right, so we want everything above 10. We want everything above 2.14. And our degrees of freedom is 13, right? Because n is 14, so degrees of freedom, 13. Get 0.026. Again, just round it however the homework wants it. This is a statistically significant result because this is less than 0.05. That means we have sufficient evidence to conclude that the null hypothesis is rejected, and we accept the alternative that mu is greater than 6. And of course, you can use stat key as well. So I'm not going to do the stat key, but you see how it works. This is very similar to what we did in the previous example, just with different numbers. All right, so that's 6 examples, and hopefully you can take that and run with it and, get the same answers when you're doing the homework and stuff. So that's the end of the section. If you want to see the shortcuts, stick around. I'll show you how to do a couple of the shortcuts. Alrighty. So let's go back. I'm going to do 2 of them. I'm going to do example 3 using the shortcuts. All right. So we're going to go, we're going to tests. This first one, we're going to do a 1 mean confidence interval. So you just want to scan through here and look for a confidence interval, and it's going to be a t interval, right? And we're just going to type the stats in. You shouldn't have to type in the data. Just type in the stats. So x bar is 10.9. S is 4.8. N is 30. Confidence level, we want 0.95. And you can see it at the top there. 9.11 to 12.69. That's what we got. So you can see that to to me, this is very fast. Remember, on the homework or a test, it might ask for the margin of error. So you need to work backwards to find the margin of error. Just take the right endpoint minus x bar for the margin of error. So 12.69 minus 10.9. That's your margin of error, right? The right endpoint minus the sample statistic is your margin of error. So we did that in section 6.1 when I did the stuff at the end of the notes. At the end of the video, I did this same stuff. All right, let's see how to do example 6 again. So, pretty similar stuff. Again, there's instructions how to do all this posted on Canvas. I just want to show you real quick. Some of you are getting the hang of this stuff real quick. This is just a t-test. Again, we're typing in the stats. Mu0 is 6. X bar, 10. S, 7. N, 14. Alternative hypothesis is greater than. And there you go. P-value 0.026. P-value 0.026. So the calculator does this stuff really fast. You could be tested on lots of different things, so you should use this really only to check your answers. I can ask you about margin of error. You know, I can have you draw the little graphs and everything. So make sure that you're still practicing all of the prerequisite knowledge. But again, it's real nice to be able to check your answers, certainly, for these. All right, well, on Canvas, there are more practice problems posted. There are videos that show you how to do all this stuff that I just showed you. If you want to use these shortcut calculator methods, go ahead and check those out. You're allowed to use them on a test. You just have to tell me what you're typing into your calculator on a test. All right, well, that's it today. And then next video will be the last one in Chapter 6. So, till next time, see you later. Study hard. Bye-bye now.